Well, hello there. Let's have a look at some more miscellaneous exercises in the area of differentiation. That is within differential calculus, and this is part 2 of a 2-video mini-series on knotty and difficult kind of questions that you can get in the area of differentiation. We'll take the sting out of their tail and we'll have a bit of fun. There's 3 examples in this video. They're all a bit annoying, so we're just going to take the sting out of their tail and make them easy for you. Now, this is example 4. Have a look at it. Just pause the video and have a look and have a go, and then we can talk about it then. See you in a moment. Okay, you're back? Alright, well, it's different, isn't it? Have you ever seen anything like that before? Well, it's quite easy, is the good news. So, I'll just show you what I would do, and then hopefully that'll help you understand how to tackle it, okay? Now, number A. This one here is a chain rule question. This is a composite function, okay? It's f of g of x, so that you know if you're trying to differentiate that, what you do is you take the derivative of f of x firstly, but not with x in there, with g of x in there instead, okay? So it's f of x but with g of x inserted instead of x, and then times the derivative of this function g of x. That's what the chain rule does, okay? So let's have a look at that. If we substitute x as 1 in there, that would make that f dashed of g of 1 times g dashed of 1. Okay, now, let's have a look at our table now and see if we can make any sense of this. G of 1. What's g of 1? G of x when x is 1 is 2. So what we can put instead of this whole g of 1 in here, we can just replace that with 2. So that then becomes f dashed of 2 times, now this one, g dashed of 1. G dashed of 1, where x is 1, is minus 1, alright? Now, what's f dashed of 2? We've got to work that one out. F dashed of 2 is 3, okay, so this becomes 3, this is minus 1, and your answer is 3 times minus 1, or minus 3. Yes, it wasn't so bad, was it? Really, it looks pretty diabolical. And if you haven't seen it before, it might throw you right off your game. But now you'll be able to do the other 3, B, C, and D, very easily. So why don't you pause the video and have a go, and then we can compare notes, okay? Okay, let's go. How did you go? Okay, B, for you and me, by the chain rule, we know that d by dx of g of f of x is g dashed of f of x, the derivative of g, but not with x in there, with f of x instead, and then times the derivative of f. Okay, that's what it is. So let's just plug and play the way we did before with number A. Okay, so substituting x is 2 this time, we've got g dashed of f of 2, that's right, times f dashed of 2. Now what's f of 2? Where are you, f of 2? Ah, you're 2, aren't you? Okay, so let's just put that down. Now, an f dashed of 2, apparently according to this, is 3. Where's f dashed of 2? My goodness, f dashed of 2 is 3. Very good. Now, g dashed of 2, where are we? G dashed of 2, this is very annoying. G dashed of 2 is 1, so it's 1 times 3, therefore the answer is 3. Excellent, alright, very good. So there's the 2 composite function ones. Now, C is actually a product rule one. Did you recognise that? Yes, so therefore when the way I teach my students is I say, okay, it's left d right plus right d left. So it's left times the derivative of right plus right times the derivative of the left one. Now we just have to substitute x is 2 for this example, so let's do that. And we get that. Now these are going to be easy to read off the table, aren't they? So what's g of 2? You look it up for me. Okay, what is it? Okay, it's 1, f dashed of 2 is 3, f of 2 is 2, and g dashed of 2 is 1. Goodness, you've got to have your head together for all this. So there it is. Now that looks like 3 plus 2, which looks like 5. Yes, absolutely excellent. Now what about D? That's a quotient rule one. Goodness, they're throwing the book at us, aren't they? quotient rule, so therefore that's bottom d top minus top d bottom over bottom squared, okay? Well, did you get that? Bottom times the derivative of top minus top times derivative of bottom over bottom squared. So bottom d top minus top d bottom over bottom squared. That's how you remember, well, that's how I remember quotient rule. So now we can just plug and play now. I'm over the screen, recapping, and here we go. Substitute x as 1. Aha! Alright, so that's what that would all be. So if you look all that up in this table up here, which is now no longer threatening to us, you get that. Did you get that? I hope so. And therefore we get that, and that comes to 5 over 4. Alright, so that's the end of that question. We absolutely demolished it, didn't we? Yes, we cleaned up. So that's very good. Let's do another example now. Now this is our special guest is making an appearance again, Mr. Modulus function. So what have we got here? If y equals log of the modulus of g of x, then what is dy dx in terms of g of x? Oh goodness, look at these mind-boggling alternatives. Well, ladies and gentlemen, it's not a problem. Let me assure you, it is not a problem. All we have to do is turn this into a hybrid function and treat each of those individually, and everything will fall into place, I assure you. Have a look at this. Now, first of all, if g of x in and of itself, the thing inside the modulus sign, is positive, then as we know, this is positive, that's positive, so therefore they're equal to each other. Okay? Right? So let's look at the other case. If g of x is negative, then for the modulus of g of x must be the negative of g of x, because g of x in and of itself is negative and the modulus of g of x is positive, so therefore a negative times an inherently negative gets a positive, and therefore this side now equals this side, right? Left hand side equals right hand side. Okay? Very good. Now, yes, that's because this is positive, this is inherently negative, and therefore negative times a negative gets you a positive. So that's correct now. Alright, now let's take each possibility in turn. We've got if the modulus of g of x equals g of x, therefore y equals log of this now, okay? Decoded without the modulus sign. Yes? Now you know by the chain rule, therefore the dy dx equals 1 over g of x times the derivative of g of x. Okay? That's how it works. Yes, 1 over the thing times the derivative of the thing, right? So that's very good. So that takes care of that one. Now secondly, if y is the log of minus g of x, which was the case if this g of x was negative in and of itself, so therefore let's do the derivative of that. Same principle, 1 over the thing times the derivative of the thing. Okay, very good. So what do we get? We get that. Now look, ladies and gentlemen, the most amazing, mind-boggling thing is that is the result, because the minuses basically become a plus, and that is exactly the same as what we got over there. Badoomch. I know, it is amazing. Truth is stranger than fiction sometimes. So therefore, we know with both cases that dy dx is just that. It's just that. It doesn't matter. And in fact, it's the same result as what you would get as if the modulus sign wasn't even there in the first place. So in fact, if you look down our shopping list of options, it's option C. Of course, you always have to have a positive function. You can't take the log of a negative function. So in fact, what the modulus sign does is just ensure that that's going to be positive, okay, always going to be positive. But the result here is the same result that you would get if there was no modulus sign there. Amazing, eh? Amazing. Yes, so let's do another one now. This is our last example for this little video. Now, my goodness. Well, fear not, it's all right. Okay, we'll do the same thing. We'll just decode this beast here, and then we'll just take the log of g of f of x. Okay, so it's not a problem, guys. Don't be afraid of them. In the previous example, yes, in the previous example, we found that if we had log of some function of x, yes, then therefore the derivative of dy dx, that is dy dx would equal that, okay, which is that, and this result is the same as if there was no modulus sign at all. That's what we were saying on the previous screen. Yes? So therefore, by the chain rule, we can say that dy dx is just going to be 1 over the thing times the derivative of the thing, and this is the thing. See? That is the thing without the modulus sign. Now this looks alright, we can't simplify that anymore, but this here we probably can. So let's concentrate on that now and then get an overall answer in a moment. Okay, d by dx of g of f of x. Now you know what to do, it's chain rule, come on. It's the derivative of g, but with f of x in there, not with x, okay? The derivative of g with f of x substituted for x times the derivative of f of x. Yes, there it is, yes? Okay, now I think that's about it, so therefore let's see what we've got. Dy dx is that thing there, which is that thing there. Now let's just have a look at our shopping list and see if it's there. No, 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 yes. Yes, big tick for number E, for you and me. There it is, there it is. So that's our answer, guys. So don't be afraid of Mr. Modulus. He's alright. You've just got to decode him first, okay? Crack the code and then everything's good. And you're a star, and go away and have confidence, and when you see a Mr. Modulus, don't worry about him. Just decode him and he just smiles, and he's very friendly from then on. Okay, I hope you got some value out of that, and we'll see you again soon. Bye for now.